is part of a microcontroller. Yeah, the major advantages here it is written. So the CPU itself, the idea of the CPU itself is to supervising and controlling the data transfer between peripherals. That's what the microprocessor does. So that if we get back to this schematic, the peripherals, so this is in general a microprocessor. So again, different classifications exist, and some people say that this is the CPU and the memory is not the part. For me during this lecture, this is the CPU itself, so the memory as well integrated into the microprocessor, while all the peripherals are connected somewhere here. So this is the basic architecture. I'll try to show you some more complex and complete as well architectures of the microprocessors, because they are different on the market. But in general, they all are around this schematic. So they are. This is really the very basic, very simple, the simplest possible schematic of a microcontroller with the peripherals here. And the microprocessor is a supervisor or a major controller in the microcontroller itself. So it's used for a configuration of the peripherals. It's interrogating peripherals about the results. It's changing the peripherals, the behavior of the peripherals by modifying the registers, and so on and so on. Although today, to be honest, the development is going towards the so-called intelligent peripherals. So today, more and more, the peripherals are operating on themselves. So without the need for constant control from the CPU side. So today it's possible also to program some peripherals. So we get, for example, in microcontrollers with wireless communication blocks, we end up with a peripheral that is actually a separate microcontroller that is communicating, delivering just the basic information to the CPU, but it's working on itself. It's so intelligent. That's of course the extreme example, but also today we have, and we'll talk about it during the semester, we've got the peripherals that are able to communicate with other peripherals without the need of the microprocessor stepping in. So the microprocessor is usually the major, the big boss of the whole microcontroller, but today its role is diminished. It's being reduced a bit. It's of course, all this is for the sake of performance. All this is for the sake of faster operation, so that we don't rely on the core itself. But also, and I will stress it out again and again, that in case of the microcontroller, in case of embedded systems, microcontroller systems which are embedded in some larger devices, it's not about the performance of the CPU that matters. Of course, it is important to have a very fast CPU in some algorithms, but quite often, maybe not in general, but quite often, the performance of the whole system is defined by a combination of CPU and peripherals, and the quality of the peripherals. So the quality, amount, number of peripherals that we have inside a microcontroller plays usually very critical role in the performance of the whole system, not the CPU itself. It's not like in computers that we must have Core i9 that is doing all the calculation. It's also not true for the large computers, but at least for the newbies, it's that processor that is the most important. It's not that. Here in microcontrollers, the CPU is important, but not really. Take a look here. We have there. It's realistic. It's ripped off a documentation of some Cortex-based microcontroller. And take a look. The CPU itself is just one block out of many. So they are the peripherals. You know, this is the real schematic, the real block diagram of a microcontroller. But the CPU itself is not in the center. It's not the largest. It's somewhere, because it's just one element of a microcontroller. That's why during this lecture as well, we'll analyze the CPU today, a bit next week, but then we'll focus on the rest. Because microcontroller is the CPU and the rest. The rest is very important. And really, the rest makes the difference between the microcontrollers. So that's why, as well, today, we've got almost everybody is building on ARM Cortex-M 0, 1, 0, 0 plus, 3, 4, 7. They are just 5 cores. Almost all IoT today is based on those 5 cores. But 5 cores, but of course hundreds of manufacturers delivering thousands of various microcontrollers, differing not by the core. 5 cores are available. Today more because we have M23, 33, 35, and 35 and then 53, but they are new cores. But the basic one are just 5 cores. But what's the difference is the number of peripherals and the quality of peripherals, and that's something, of course, we will tackle during the semester. But then, before we go there, before we start with the peripherals, with the analysis of the capabilities of microcontrollers, a step back towards the to the introduction to microcontrollers, to the microprocessor itself. What is a microprocessor and the basic elements? And the basic elements of the microprocessor, so something that we already somehow discussed. So, a microprocessor, to make it short and brief, first of all, is a programmable device that has a fixed hardware, but a device that's functionality is defined by the software. So, you remember, I hope, logic, finished state machine, and the finished state machine with data path and the CPU. But the CPU is in fact a finished state machine with data path where the finished state machine behavior is changed by the program. It's changed by the inputs, and on the inputs we have the program. That's why it's a programmable device. That's the difference between the CPU and the FSMD. Because the FSMD, the classic FSMD, has a fixed functionality. So it's a finished state machine with data path, so we have a data path, we have a finished state machine, but the finished state machine has a behavior which is fixed. Here, in case of microcontroller, the only difference in fact is, and that's what I was showing this during last lecture, previous semester, we have a stream of data, we have a program following, changing the finished state machine, changing the behavior of the finished state machine. So that's why it's programmable. Of course, it's digital. There used to be ideas of doing analog microcontrollers, and one block of these ideas is still with us. We are using the operational amplifier. The op-amp, the idea of op-amp, of operation amplifier, was to be a building block of an analog microprocessor. There were such trials of how to do the analog microprocessor. They failed. It was, of course, in 1950s, 60s, something like this. It failed, so because there are too many difficulties with building analog microprocessor, working on analog signals, so that we input two analog signals and then we subtract it, divide it, multiply it, make a logarithm. In my high school, I finished my finished work for high school was to construct such analog microcontroller based on the operation amplifier, a simple one, of course. It worked, but of course with so many limitations it was useless for normal operation. That's why today, digital world, digital data, that's of course quite normal. Processes data according to instructions stored in memory, that's why programmable device, results their outputs, and everything in binary numeral system. We talked about the previous semester, binary system, because of course it's simple and efficient to make a two-state system. So it is again possible to make a decimal system, for example, but it's completely impractical and error-prone. In case of binary system, have two simple states, closed and open. And that's how it is working. Main elements of the microprocessor, everything is working around the data path. It's a data path because we talk about FSMD as the ancestor of the simpler step of the CPU. So the arithmetic logic unit is this data path. So the data path that has inputs of data stream and outputs a data stream. This arithmetic logic unit, the behavior of this unit is controlled by the instruction decoder. So instruction decoder is taking the stream of instructions from the instruction memory, and this stream is then driving the behavior of the arithmetic logic unit. And again, just two elements here, the CPU. Instruction decoder and arithmetic logic unit, two major blocks, and must-have blocks inside a microprocessor. The other blocks are just helping elements. So the elements that are extending or making the operation of the microprocessor possible, but yet theoretically they are not necessary. Theoretically, like in FSMD, because it's not that we have FSMD and there is nothing and we have CPU. There are 50 shades of gray, as they say, so something in between. Always there is, between one and the other. It's not black and white. So what are the other elements? What is the purpose? Let's analyze them step by step. So arithmetic logic unit, the element that is usually depicted as graphically as something like this. An element that has data inputs and data output, plus an input of instruction and the output of status. That's what all the letters mean. So A, B are inputs, and R output, F is the instructions. The status, the A, B, and R, the width of those inputs and outputs are defining if our microprocessor is 8-bit, 16-bit, 20-bit, 24-bit, 32-bit, 64-bit. We can have another one even. So in programmable logic, we can build a 3-bit processor or 11-bit processor by changing the width of those A, B, and R's. It is possible. Although, from practical point of view on the market, usually we have either 8-bit or 32-bit processor in case of microcontrollers. But there exists also a large group. There exists a large group of 16-bit, and slowly, very slowly, in case of IoT, in case of microcontroller world, 64 bits. Although 64 bits are not very popular because there is no real use, at least for now. So it's happening in large computers, but in microcontrollers, not really. It's not yet come. It's not yet come. So 64-bit, not in this world, not yet. I'm waiting for this, really eagerly. But no, the world is going towards multiple core, towards parallel architectures like SIMD or even MIMD, but not really towards 64. That's how the world is going. We'll see during next forthcoming years what's going to happen. But at least that's the state for now. 8, 16, or 32-bit. There used to be 4-bit microprocessors in the market, but they are not, of course, available anymore. In case of arithmetic logic unit, this block is usually quite simple. It's usually delivering basic arithmetic operations, honestly, without multiplication and division. So I put the multiplication and division here, but as you should remember from introduction to microcontrollers, multiplication and especially divisions are very resource-hungry operations. And to make them single-cycle operations, in case of division, I don't think it's even possible. But for multiplication, it's theoretically possible to make a single-cycle multiplication, but that requires a horrible amount of logic, of components. That's why, to make everything simple and concise, quite often the multiplication and division are delivered by separate processor, we call it, separate model which is used just for calculation of multiplication or just for calculation of division. It's less often. Normal arithmetic logic unit is not usually delivering this kind of functionality. The multiplication itself requires more logic elements than all the other operations together. Because what are the other operations? Addition, subtraction, comparison, and various logic operations like negation, ending, ORing, sorry, this kind of stuff. Auxiliary registers, auxiliary elements to the microprocessor, because we mentioned about two major ones, so arithmetic logic unit and instruction decoder, but there are also auxiliary elements. One of the auxiliary elements is status register, always present in microcontrollers. and microprocessors, various kinds. This is the element where the major functionality of status register is to be a temporary storage of status data of arithmetic logic unit. Because for example, if we try to add two numbers to 8-bit numbers, and yeah, let's consider the 8-bit microprocessor, and we try to add 200 and 200. The result is 400, but 400 is outside the range of 8-bit number, which is 255. Which means that we have kind of special situation. This special situation is handled by notifying it somewhere, storing it somewhere in this so-called status register somewhere. So this is actually the carry or overflow, depending on the operation. For example, we may need to compare two numbers. So if two numbers are same, lower, which one is lower, higher, whatever. Again, the result of comparison has to be handled somehow. And this is handled, this is delivered to the output, not by in any way, in any point here, but the result of comparison is given in D. And this D is then stored in the status register as negative or 0, for example, because then the result of comparison is negative or 0. These are the bits used for comparison. Today, in case of microprocessor, that's the basic functionality. But today, status registers in many microcontrollers on the market are used not only to depict the status of the processor itself, but also to depict a status of a microcontroller. Quite often, in case of microprocessor, we've got some flags about the interrupts, like here in this example we have GIE. IE stands for interrupt enable. So there is always some major interrupt. Today, it's not necessary for a microcontroller to be, the status register doesn't need to include it, but there, almost always, it includes the flags like actually the interrupt flag or some power supply options. So here is oscillator off, CPU off, for example. Yet these are not a must-have. The must-have in status registers are the basic flags like NZ, CV, H, and sometimes some other status flag from the arithmetic logic unit. Next auxiliary element, not necessary, but always available, or almost always available. It's a stack pointer, part of a microprocessor. And we always need to store temporary data somewhere during calculation. So this from practical point of view. Quite often that whatever we count, we need to put it somewhere to the side, then return back to this later. And this is so frequent, this is so often, then this mechanism was made available in the microcontrollers today. What is a stack? Stack is, as the name suggests, a structure which is last in, first out. So the structure which is called LIFO structure. Last in, first out. But the LIFO structure here is hardware supported usually. Hardware supported means that we don't need to do it in software, this LIFO structure, but this LIFO structure is supported directly by the instruction inside the code. Which means that first of all we've got special instructions. I will show you the instructions next week. Special instructions for placing data onto the stack and getting data back from the stack, but also this stack plays a very crucial role in this application, in storing return addresses in various subroutine calls. Without stack, we are not able to make any nesting, any procedures nesting in the microcontroller. So we would not be able to write down, maybe not recurrent software, but even simple software where we call functions, so that we call a function and then the function call another function. Because the stack is used to remember the return address, where to return to. So that's what the stack is for. So the stack pointer, the stack is implemented usually as growing from higher locations to lower memory locations. So it's also usually that we put the stack at the bottom of the memory, so it's growing up, and then at the same time we are using variables on the top of the memory, and we pray that it doesn't meet because it leads to a catastrophe. But more about the stack, I think, will gradually extend the stack functionality and what's the difference between stack and heap during the semester. Program counter. Something that we mentioned already during last lecture, from introduction to microcontroller. This is the register that is pointing to the next address of the memory, of the program memory. A simple thing, simple element, yet something that is always existing. So it is pointing to the next instruction, and the program execution. It's an element that we cannot neglect in the program execution, because it's pointing to the next instruction, and it's incrementation or changing of the value of the program counter causes the various behaviors, important behaviors of the program, like jumps, like calls of the subroutines, because the jump to another subroutine basically is a change of the program count. So it's as simple as this. So this is a simple thing, simple element. Usually one register. The width of this register to be one small remark. The width of this register, if A, B, and the R on the slide that I showed a bit before, the width of those signals define us if the microcontroller is 8-bit, 16-bit, or 32-bit. Thus, the width of the program counter tells us the addressing space of the microprocessor. So how long a program can be, it's defined by the program counter, by the width of the program counter. So the program counter, the width of the program counter is never as short as 8-bit. I have never seen a microprocessor that has a program counter which is 8-bit. The program counter is usually 10-bit, 11-bit, 12-bit, 30-bit, 15-bit. It's also very rarely this 8, 16, or 32-bit width. It is in some microprocessors, but quite often we've got the program counter width which is strange, like 14-bit. But 14-bit means that the microprocessor with 14-bit program counter is able to address 2 to the power of 14 cells, which is not very much, because it's just like 16,000. But it can address 16,000 cells. Then if the cells are 8-bit, 16-bit, or 32-bit cells, then it is defined by A, B, and R. But program counter is something different. It defines it. So if we know the width of arithmetic logic unit input and outputs and the program counter, that we know how much memory can be connected to the program, to the microprocessor, so that the what's the size of memory map of the microprocessor. So these two elements are defining for us the memory map size. Then we come to the instruction decoder. So the instruction decoder actually does 3 things. The instruction decoder. So the instruction decoder must get the instruction. So fetch, very nice word. Fetch the instruction from the memory in some way. Then it has to decode the instruction, and then it has to put it into the execution. What is important is that the execution doesn't need to be with the use of arithmetic logic unit. The functionality of instruction decoder is superior than the functionality of arithmetic logic unit, because ALO is a stupid executor of what is given by the instruction decoder. So I like to think about the instruction decoder as the brain of the operation, because the capabilities of the instruction decoder tells us about the capabilities of our microprocessor very much. Because what kind of instruction is it able to decode? That's the functionality of the microprocessor. Some microprocessors have the decode part, which is able to decode just a very, very simple instructions like add, like move, like load, like store. And some microprocessors have the instruction decoder, which is able to make, for example, automatic copying of certain elements of the memory, or make a multiply and accumulation of parts of the memory, not even of one cell or one register, but of parts of memory. All this is hidden actually here. So the complexity of the decode part of instruction decoder is giving us this functionality of the whole microprocessor. So this is really a crucial element, or the most important element, I would say, of every microprocessor that you can think of. Also, the fetching part is important, because fetching theoretically is simple. So yeah, we read the memory. So we have a program counter. The program counter puts changes the address, changes the pointer to the memory, and then we just read through the data bus the value inside the memory. But that's simple in 8-bit microprocessors. But if we start working with clocking speed of 16, 20, 24 megahertz, but if we go towards hundreds of megahertz, which is the case today, if we want to parallelize operations, which is the case today, then the fetching itself, it's not so simple anymore. That's where, for example, cache begins, because the cache is a kind of a fetch supporting memory, which speeds up the fetching process, because this fetching process, in case of hundreds of megahertz microcontrollers, and in case of parallel operations or superscalar, so-called superscalar processors, then the fetching becomes the element that has to be improved and has to work better, not just simple get from this cell 1 byte of data. So this whole part, we will analyze it for sure again in case of, for example, elements extending the instruction decoder capabilities like pipelining. We will analyze it next semester. It's not time for this during this semester. Although, of course, part of this analysis will already appear next week, because STM8 has kind of pipelining. So also to explain how it works, how the STM8 core works, we will need to introduce some parts, at least, of this three-phase operation of instruction decoder. And the last from those important elements, almost the last, because I would like still to add one more, to introduce one more element, are registers. Registers, also the memory used for storing temporary data. Like stack pointer, but this time not stack, but dedicated memory. Yeah, should be a question, what the hell is the difference? The difference is that the registers, it's the same kind of memory like stack pointer. In some microcontrollers, it's physically the same silicon. Completely physically the same silicon. Just different addresses, so different areas of the same silicon in some microcontrollers. The registers and the static memory where the stack pointer is hidden. But the registers, what is special about the registers is that they are specially available. So they are treated specially. So they are available in addressing modes, in short addressing modes. They are available. Oh, maybe this way. So the access to those registers is simplified, simpler from the application point of view, simpler and faster. So stack pointer is fast. So using stack is fast, but the stack is first of all it's a LIFO structure. In some applications, LIFO structure is very good. In some applications, like calling functions, calling procedures. In case of registers, we don't have sequential, but LIFO, you know, it's sequential access. So the best for LIFO is sequential access, so that we put on stack a sequence of data and then get back from stack a sequence of data. In case of registers, it's better for random access. So it's better for random access, and as well for random access, because it is inherited, the so-called inherited addressing modes are used to access the registers. Also, this access is faster. The random access to these registers is much faster. So the registers are, in general, normal static memory elements, but with dedicated addressing modes, making the use of registers very fast. And there is one last element which I'm missing here actually, because I always forget to add a slide about it. but it's also an element that I can't imagine a microprocessor to be constructed without. This is an interrupt. These are interrupts or interrupt controller. So this is the element number 6, which is also auxiliary. So instruction decoder and arithmetic logic unit must have program counter, program stack, registers, and the 4th element, auxiliary one, is the are the interrupts and the interrupt controller, because the interrupt controller is usually external of the microprocessor. But in general, the idea of interrupt and the support to interrupt. This is very important element of each microprocessor today, which it's almost impossible to use a microprocessor today effectively without an interrupt. We'll talk about the interrupts in 2-3 weeks. I mentioned about it because we will start with the timers and interrupts. That's why we'll start with it, because it's so important. To give you an idea how important it is, in the microcontrollers that I started my education with 20 years ago, something like this, those microcontrollers were supporting a couple of interrupts. An input, so interrupt could be generated or was recognized out of just a few inputs. Today's microcontrollers are capable of recognizing thousands of inputs. Interrupts coming from thousands, not thousands, but thousands of inputs. It shows how much important the interrupts are today in microcontroller world. So if we are using computers, it's hidden, but in microcontrollers, we are always hit by the interrupts and the need to use the interrupts, in real applications. Program flow. So what's happening inside? This slide was already shown, I think. Unfortunately, the colors are not clearly visible here on this beamer. But what is happening? What we have here, very basic educational microprocessor. A microprocessor with all the elements necessary that we mentioned about. Take a look. We've got the arithmetic logic unit, which is controlled by instruction decoder, which grabs or fetches the program from the program memory. There is a program counter which is pointing to this program memory. Take a look. Program counter 10-bit, which means that it is possible to address 1024, but mind that, words, not bytes, but word. Word. Again, be careful here. Word, if byte is always 8-bit, byte is a byte, but word in this world of microcontrollers, it's not 16-bit, it's not 32-bit, it can be anything. Sometimes word can be even 8-bit, although this is not very frequent. Usually 8-bit is reserved for a byte, but word can be of any. It can mean anything. A word in this world, word and world. So here in this microcontroller, word is 18-bit. So it means that the memory is not 1000 kilobytes, but it's about 2.3 kilobytes, because if this is 18-bit, so you can multiply 1024 by 18 and then divide it by 8, and then you get the number in kilobytes. But the most important is 1024 words. And here we have the registers. Of course, we've got the input and the output. So a classic of the microprocessor. So we have input data, output data, and the program. So here is the data path, and here is feed state machine, so FSMP. And how it works in case of microprocessor, after reset, so program flow is very simple. After reset, program counter is set to some value. Can be 0, can be anything. Because it really depends on the manufacturer, on the engineers. Yeah, the engineers sit, buy a cup of coffee or a beer, and say, okay, let's make a microcontroller starting at 100. Why not? And then it starts from 100. So it means that after reset, the registers because they are usually, it's a simple register usually. So the registers here are initialized in hardware, by hardware, physically, are initialized to some value. It can be really any value. It's not, I can't say that it's always 0, always FFF. It's some value. And this is the starting point. And it means that in the program memory, at this starting point, there must be something. So we always, when we start with new processor, when I start with a new processor, one of the things that I do is check out what's the initial value of the program counter. And then when I write the software, I must put under this address something. Because this is the starting point, this is the initial point. Execution starts from this point, because the first instruction that the instruction decoder fetches is from this address. Then the program counter there is a program flow control. The program flow control means that it either increments the program counter if nothing special happens, if no special instruction happens, but if there is a special order from the instruction decoder, then the program flow controller modifies the program counter, either changing its value not by 1, but by 2, 5, 10, 20. These are so-called branches. So this is branch in usually the assembly instructions of branching, or changes it completely. These are instructions like call, go to, jump, whatever. So then it changes it from 0 to whatever value we need, and then the program, of course, jumps from here to here. If they're normal instructions, so depending on the instruction, we may have either changed the program counter, there may be the needs to use the program counter stack, there may be some arithmetical logic operations, or there may be some instructions influencing directly the ports, input and output ports. More about the operations, about what kind of instructions are available in microprocessor, what group of instructions are available in a standard microprocessor. More on this already next week. In case of the instructions, they are physically they are numbers, because the instructions, how we can expect here, this is a program memory. So we talked about it last semester. So this is physically a memory. So physically bits of zeros and ones. So a matrix of values. But naturally it would be completely it would be very, very difficult to write a software using numbers. So that's why in real life we've got so-called mnemonics. So we've got the descriptions, some abbreviations of operations, which are translated directly to numbers. Again, I'll show you next week where to find those values, because it's not a problem if you write on the microcontroller. There is always an instruction with a table that is showing us the direct translation between the assembly language, we call it assembly language, and the mnemonics, and the machine language, because the values, the numbers are this is so-called machine language. Imagine that in 1970s, the people were using the machine language to program. I'm not that old, but I saw the code, which was, people were sitting and really they were using machine language, so they were using numbers. Today we are even not using this one, so we are actually, during this course, I really want you to play with assembly language so that you have some knowledge that something like this exists, because to be honest, today even this language is forgotten. So we don't use it because it's a waste of time, in my opinion as well. It's a waste of time in professional life, when you are doing some physical project. But here, for the education, it does have a sense, in my opinion. That's why I would like you to have some experience in this and during the laboratory, and we'll analyze this a bit next week as well. And then we come to, if we talk about the program counter, the last element today, then we must have also the memory map itself and the structure of the processor itself defines for us an element which we call a program map, a memory map. The memory map is showing us what kind of memory is addressable under which addresses, and how to get to certain parts of memory. Because sometimes we've got a situation like in this memory map where everything is accessible just under different addresses. This is so-called memory map. We've got different addresses, and then under this address is data. Under this address there are some static RAM, there are peripherals. Here are another peripherals, another static RAM, and so on and so on. Whatever is here is not that important. Or we might have situations that we have at the same address, we've got different memory, and we have to use different instructions to get to different memory. It really depends on the structure of the microcontroller, or microprocessor, microcontroller. We'll talk more about it a bit later. It's a bit too early to talk about the memory map details, but again, this is an element of the microprocessor that is necessary to understand what we put it for the later. And we'll put it for the later during this semester. So that would be it for today. So thank you for your attention. It was very glad to see you all in person. Hope to see you again.